Today, we are going to be discussing the lever. It is one of the 6 simple machines that we are going to be learning about in our mechanical advantage unit. Over 2,000 years ago, Archimedes of Syracuse understood that if he had a lever long enough, he could potentially move the earth. This quote exemplifies the understanding of how a lever provides mechanical advantage and a force amplification. A lever is a machine consisting of a beam or rigid rod pivoted at a fixed hinge or fulcrum. A lever amplifies an input force to provide a greater output force, which is said to provide leverage. The ratio of the output force to the input force is the ideal mechanical advantage of the lever. Mechanical advantage for a lever is calculated by dividing the distance from the fulcrum to the effort by the distance from the fulcrum to the load. We can see that in this graphic. The equation for mechanical advantage is length to effort divided by length to load. That measurement is taken from the fulcrum. So, in this case, the fulcrum to our force of A is our length to effort. The length to load is from the fulcrum to F sub B, which is our load, our weight that we're trying to move. We can see in this sample that the distance from the fulcrum to the force that's applied to the effort side of the lever is 12 inches. We can also see that the distance from the load to the fulcrum is 6 inches. We can apply these variables to our equation by replacing length to effort and length to load. In this case, mechanical advantage equals 12 inches divided by 6 inches. The inches will cancel out, and we will be left with a simple fraction of 12 divided by 6. We can simplify this fraction as 2, and therefore, in this example, mechanical advantage is equal to 2. Again, the mechanical advantage of a lever is equal to the length to effort divided by the length to the load. In this graphic, you can see 3 different classifications of the lever. In a class 1 lever, the fulcrum is at the middle and the load and the efforts are at each end. As you can see, the fulcrum is closer to the load than it is to the effort. As a result, it requires very little effort to overcome a large load. In a class 2 lever, the fulcrum is at one end and the effort is at the other. Because the load is in the middle, it will always amplify the force of the effort to overcome the load. In this case, you can see that a small effort is applied to move a large load. However, in a class 3 lever, the fulcrum and the load are at opposite ends of the beam or lever, and the effort is located in the middle. In this case, the effort will always be more than the load to be moved. As you can see in the graphic, there's a relatively small load, but it requires a large effort to move that load in a class 3 lever. In the graphic to the left, we can see different applications for where we might use these levers. In the class 1 lever, we might use a lever to move a large object provided that the fulcrum is close enough to that large object, in which we would have an amount of force amplification. In a class 2 lever, we see a common example of a wheelbarrow. A wheelbarrow always has the load in between the fulcrum, which is the wheel and axle system, and the handle. Therefore, lifting a heavy load with a wheelbarrow is normally not that difficult. Lastly, we use heavy equipment to move earth materials, and therefore we have to apply a very large effort to move a medium-sized load in this application.